Our journey into the heart of black holes has revealed them to be cosmic giants, shaping galaxies and providing the most extreme gravitational laboratories in the universe. But what if the story began with much smaller, more exotic black holes? What if the universe's history is peppered with tiny primordial black holes, remnants from the fiery crucible of the Big Bang? The theory is compelling. In the first moments of the universe, conditions were so hot and dense that vast fluctuations in energy and pressure could have compressed some regions of space-time so violently that they collapsed into black holes. These are primordial black holes, and they could have a huge range of sizes, from as small as a single atom to as massive as our sun. If they exist, they could be everywhere. Invisible specks of pure gravity scattered throughout the cosmos. So far, however, we have found no definitive evidence of them. This is one of the universe's great cosmic mysteries. Where are all the primordial black holes? The search for them is a cosmic detective story. We're looking for their effects on their surroundings. A tiny primordial black hole passing through a star or even a planet would have a dramatic and detectable impact. We're searching for the unique gamma ray bursts that would signal their final evaporation, a fleeting burst of light as they blink out of existence due to Hawking radiation. But their very absence is also telling. The lack of detected primordial black holes places a powerful constraint on our models of the early universe, helping us refine our understanding of its first chaotic moments. It's a case where the missing evidence is just as important as the evidence we find. Before we start this journey into the cosmos, please consider liking this video, sharing it with others, and subscribing to our channel for more awe-inspiring explorations. We'd also love to hear from you in the comments below. Where in the world are you watching from, and what time is it for you right now? Now, get ready and relax. Black holes are not just masters of space. They are also masters of time. Einstein's general relativity predicts a phenomenon called gravitational time dilation. The closer you are to a massive object, and nothing is more massive in a small space than a black hole, the slower time passes for you relative to someone far away. For a black hole, this effect becomes extreme. As you approach the event horizon, your clock would slow down to a crawl compared to a clock on a distant spaceship. If your friend watched you fall into the black hole, they would see you move slower and slower, your movements becoming infinitely lethargic as you reached the event horizon, where you would appear to freeze forever. This mind-bending concept opens up a tantalizing, if highly speculative, question. Could black holes be used for time travel? The theoretical answer, according to our current understanding, is a qualified yes, but only in one direction: forward. If you were to spend a week orbiting a black hole, very close to its event horizon, and then return to Earth, you would find that decades or even centuries had passed for everyone else. You would have effectively traveled into the future. This isn't just science fiction. Satellites in Earth's orbit, like the ones in the GPS network, have to account for tiny amounts of gravitational time dilation caused by Earth's mass. If they didn't,
our GPS navigation would be wildly inaccurate. A black hole simply takes this effect to its most extreme and profound conclusion. But what about traveling backward in time? That's a different story.
Theoretical solutions to Einstein's equations have even suggested the possibility of wormholes. A wormhole, also known as an Einstein-Rosen bridge, is a theoretical tunnel through space-time that could connect two different points in the universe, or even two different universes, in an instant. Some physicists have speculated that a special type of spinning black hole, known as a Kerr black hole, could, under the right conditions, theoretically serve as the entrance to a wormhole. The incredible rotation of a Kerr black hole twists space-time in a way that could, in theory, create a stable tunnel. But here's the problem. To keep a wormhole open and traversable, it would require a form of exotic matter with negative mass or negative energy. This is a substance that repels gravity, an idea that exists only in the realm of pure theory. We have no evidence that such matter exists in our universe. Furthermore, any attempt to travel through such a wormhole would be incredibly dangerous. The slightest disturbance could cause it to collapse, destroying the traveler. The immense tidal forces would also spaghettify a traveler before they could even enter. So, while the idea of a black hole as a cosmic shortcut is a tantalizing one, it remains firmly in the realm of speculative physics. For now, the universe's shortcuts are off-limits, shrouded in the mysteries of gravity and quantum mechanics. We've discussed how supermassive black holes can shut down star formation, but the story is more nuanced. Black holes can also be powerful engines of creation. The same powerful jets of particles that can prevent star formation in a galaxy's central region can also trigger it in the galaxy's outer reaches. As the jets plow through the cool intergalactic gas, they create shock waves. These shock waves compress the gas, making it dense enough to collapse under its own gravity, triggering a new burst of star formation. This is a stunning revelation. The same object that can act as a cosmic sterilizer in one region can be a stellar nursery in another. It's a testament to the complex and dynamic interplay between black holes and their host galaxies. They are not just passive inhabitants, they are active architects of galactic evolution, shaping the very structure and life of the galaxies they inhabit. The black hole at the center of a galaxy acts as a kind of cosmic regulator, controlling the ebb and flow of gas and dust that fuels both itself and the birth of stars. This dance is a key to understanding how galaxies came to be the beautiful spiral and elliptical structures we see today. Our understanding of black holes has advanced dramatically, but the journey is far from over. The next generation of telescopes and observatories promises to reveal even more of their secrets. The James Webb Space Telescope, with its unparalleled infrared vision, is peering back to the dawn of time, searching for the very first quasars and the seeds of the first supermassive black holes. It's a cosmic time machine, giving us a glimpse of a universe when the first stars and galaxies were just beginning to form. Meanwhile, gravitational wave astronomy is entering a new era. Future observatories like the LISA, or Laser Interferometer Space Antenna, mission will be a trio of spacecraft flying in formation in space,
forming a giant triangle millions of kilometers on a side. LISA will be sensitive to different frequencies of gravitational waves, allowing it to detect the mergers of supermassive black holes, the most violent and powerful events in the universe. It will be our ear for the cosmic symphony of black hole collisions, revealing secrets of galactic evolution and the nature of space-time itself. And on the ground, the Event Horizon Telescope is not finished. With new telescopes and improved technology, we are poised to create a movie of the M87 star black hole, showing how its fiery ring of light changes over time. We also hope to capture an image of our own galaxy's central black hole, Sagittarius A star. Imaging a black hole with a more active and chaotic accretion disk will provide a new kind of challenge and a new wealth of information. We are still at the very beginning of our exploration of these cosmic enigmas. Every new tool, every new observation brings us closer to unraveling their mysteries. Black holes remain the ultimate puzzle, a beacon for human curiosity, drawing us to the edge of what we know and challenging us to imagine what lies beyond. We have gazed into the abyss with the Event Horizon Telescope, and we've listened to the universe's deepest rumbles with LIGO. But what if we've only been hearing the tip of the iceberg, the most violent, energetic collisions? What about the constant, low-frequency hum of countless ancient black holes merging across the cosmos? The universe, it seems, has its own silent symphony, a background hum of space-time itself. Scientists are now on a quest to detect this gravitational wave background. It's not a loud chirp from a single event, but a continuous stochastic noise, like the collective sound of a distant, massive crowd. This cosmic hum would be created by the billions of supermassive black hole mergers that have occurred throughout the history of the universe. To detect this, we need a new kind of observatory. Astronomers are using an ingenious method called pulsar timing arrays, or PTAs. A pulsar is a rapidly spinning neutron star that emits a beam of radio waves, much like a cosmic lighthouse. As the pulsar spins, its beam sweeps across Earth, giving us a highly regular and precise pulse. These pulses are so predictable that they can be used as cosmic clocks. Imagine a network of dozens of these clocks spread across our galaxy. If a gravitational wave passes between us and a pulsar, it will slightly stretch or squeeze space-time, causing the arrival time of the pulsar's pulses to be delayed or advanced by a tiny fraction of a second. By meticulously monitoring a large array of pulsars, scientists can look for a correlated pattern of these timing changes. It's like finding a single, slow-moving wave in the ocean by watching how a network of buoys bobs up and down. In 2023, several independent PTA collaborations announced that they had found a strong signal consistent with this gravitational wave background. The evidence suggests we are finally hearing the low-frequency rumble of the universe, a testament to the immense power of supermassive black hole mergers. This discovery provides a new way to study the cosmic history of black holes and the evolution of galaxies themselves. We've discussed how black holes are the architects of galaxies, but their relationship with individual stars can be far more violent. When a star stray is too close to a supermassive black hole, it can be subjected to a terrifying process known as a tidal disruption event. Imagine a star orbiting its galaxy center, minding its own business. Suddenly, a gravitational hiccup in its orbit sends it hurtling towards the central supermassive black hole. As the star crosses a critical boundary, the black hole's immense tidal forces, the same forces that cause spaghettification, take over. The side of the star closest to the black hole is pulled with far greater force than the side farthest away. The result is a cosmic tug-of-war that the star can't possibly win. The star is ripped apart in a spectacular display, a process some have called a cosmic sneeze. The stellar material is stretched into a long, luminous stream of gas, some of which is flung out into space, while the rest spirals inward to form a new accretion disk around the black hole. As this material is compressed and heated to millions of degrees, it emits a powerful flare of light, particularly in X-rays and UV radiation that can outshine the entire galaxy for a time. These TDEs are incredibly rare, but they are a powerful confirmation of a galaxy's central black hole. They are the cosmic equivalent of a dinner bell, signaling to us that a supermassive black hole is actively feeding. By studying the light from these events, we can learn about the properties of the black hole, the composition of the star it devoured, and the extreme physics of matter under the most intense gravitational stress. Stephen Hawking's prediction of black hole evaporation, Hawking radiation, remains one of the most profound and unproven ideas in modern physics. If true, it means that black holes, the universe's ultimate prisons, are not eternal. They slowly leak energy and particles back into the cosmos. But how can something that can't be escaped emit anything at all? This is where the strangeness of quantum mechanics comes in. Even in the vacuum of space, particle-antiparticle pairs are constantly popping in and out of existence. These are virtual particles, fleeting existences that normally annihilate each other instantly. However, near the event horizon, a strange and terrible thing can happen. A virtual pair can pop into existence right at the edge, with one particle falling into the black hole and the other escaping. To an outside observer, it looks as though the black hole is emitting a particle. In essence, the black hole is using its gravitational energy to create a real particle from the vacuum of space at the cost of some of its own mass. The implications are immense. It means that black holes are slowly shrinking, and the smaller they are, the faster they evaporate. A stellar mass black hole would take an almost unimaginable amount of time to vanish, far longer than the current age of the universe. But a tiny primordial black hole, created in the early universe, could be evaporating in a flash of gamma rays right now. Detecting Hawking radiation is one of the holy grails of astrophysics. It would be a direct observation of the intersection of general relativity and quantum mechanics, a test of our most fundamental theories of reality. If Hawking radiation is real, it leads to one of the most perplexing and debated questions in all of physics: the black hole information paradox. The paradox is this: quantum mechanics dictates that information can never be truly destroyed. It might be transformed or encoded, but it must be preserved. Yet, if a black hole evaporates into generic thermal Hawking radiation, what happens to the information about everything that fell into it? The atomic structure of the star, the history of the astronaut, the very quantum state of the particles themselves? Does all of that information simply vanish from the universe? This is a direct conflict between general relativity, which says information can be lost, and quantum mechanics, which says it must be conserved. Resolving this paradox has become a central challenge for theoretical physicists. Some believe information is indeed lost, which would mean quantum mechanics must be modified at the black hole's boundary. Others propose that information is somehow encoded on the event horizon itself in a way that we don't yet understand, and slowly being leaked out in the subtle variations of the Hawking radiation. This is a key component of the holographic principle. Still others, including Stephen Hawking himself in his later years, suggested that the information might be stored in a kind of hair on the black hole's event horizon, a concept he and others explored in detail. The information paradox is a cosmic riddle that will likely require a complete revolution in our understanding of the universe to solve. It's a reminder that black holes are not just strange objects in space, but the ultimate testing grounds for the very fabric of reality. Our journey into the heart of black holes brings us to their most iconic and enigmatic feature, the event horizon. This isn't a physical barrier, but a boundary of no return, a cosmic threshold where the very fabric of space-time itself becomes so warped that nothing, not even light, can escape its gravitational pull. Imagine a river flowing faster and faster. At a certain point, the current becomes so strong that no boat, however powerful, can paddle upstream.
Gravity's trap, falling forever into the abyss. What does it mean to fall and never stop? When we think of falling, we imagine something simple: a stone slipping from our hand, a leaf drifting to the ground, even ourselves tripping for a brief, heart-stopping moment before our feet catch the earth again. Falling, in our everyday world, is always temporary. It always ends with something solid beneath us. But in the universe, there are places where falling never ends, where gravity is so powerful, so absolute, that once you begin the plunge, there is no return. These places are black holes. A black hole isn't an object in the ordinary sense. It's not a planet, not a star, not even a thing in the way we usually understand things. It is better thought of as a region, a place in space where gravity has collapsed everything into a singularity, a point of infinite density where the known laws of physics break down. Surrounding this singularity is the event horizon. This is the ultimate boundary, the point of no return. Once something crosses it, a rock, a spaceship, or even a beam of light, escape is impossible. And that's where our story of falling begins. Imagine you're watching a friend fall into a black hole. From your safe distance, what would you see? You might expect them to plunge in quickly, disappearing past the horizon like someone vanishing underwater. But that's not what happens. Instead, time itself plays a trick. As your friend approaches the event horizon, their movements slow, slower, until, to your eyes, they seem frozen in place. Their image lingers, stretched and dimmed, fading into a ghostly shadow. They never quite cross. To you, they are suspended at the edge of forever. This is because the immense gravity of the black hole warps time itself. To you, on the outside, their clock ticks slower and slower, approaching a standstill as they near the horizon. But from their perspective, their fall continues without pause. They cross the horizon in seconds. For them, time feels normal. It is only the universe outside that seems to accelerate, racing into the future at an unimaginable pace. So let's step into the traveler's shoes. What does it feel like to fall into the abyss? At first, perhaps surprisingly, not much. If the black hole is large, say millions of times the mass of the sun, you wouldn't notice anything unusual as you crossed the event horizon. There's no sign, no physical surface, no sudden change. One moment you are outside, the next inside. But as you continue inward, gravity begins to reveal its brutal hand. The pull on your feet is stronger than on your head. This difference is called tidal force, and near a black hole, it becomes extreme. You are stretched, elongated, pulled into what physicists grimly call spaghettification. Atoms, molecules, even the very fabric of your body would be torn apart. Closer still, not even atoms survive. Matter itself is shredded, energy released in violent bursts as you are absorbed into the singularity. It's a journey without return and without an end in the ordinary sense. You don't land, you don't arrive, you simply become part of the black hole. Now here's the paradox. To you, the traveler, this fall may only take seconds or minutes, but to an outside observer watching from afar,
Your fall takes forever. They will never see you cross the horizon. Instead, your image lingers, stretched, across time, fading ever slower. It's as if the black hole traps not only matter, but also the story of everything that falls into it. The shadow of your fall is etched on the surface of the universe itself. This paradox of a fall that both ends quickly and never ends at all is one of the many mysteries that make black holes so strange, so captivating. The idea that gravity could trap light itself was first considered in the 18th century, long before Einstein. But it was Einstein's theory of general relativity in 1915 that revealed the true depth of this trap. Einstein showed that gravity isn't a force pulling objects through space as Newton imagined, but rather the warping of space and time itself. Mass bends the fabric of the cosmos. The greater the mass, the greater the bend. A black hole is what happens when that bending becomes infinite, when space-time folds in on itself so completely that escape is impossible. And one of the strangest things about black holes is not just what happens inside them, but what happens to our knowledge outside them. The event horizon isn't just a physical boundary, it's an informational one. From our perspective, we can never see beyond it. We can never know what lies inside. Every signal, every photon of light, every whisper of information is trapped. It is as if the universe itself draws a curtain, saying, "Here, knowledge ends." This is why black holes are not just objects of science, but also of philosophy. They force us to confront the limits of what can be known. Let's return to the fall. Why does it seem eternal from the outside? It has to do with how light escapes the black hole's gravity. As your friend falls, the light from their body struggles to climb out of the deepening gravitational well. Each photon loses energy, shifting to longer and longer wavelengths. The image grows redder, dimmer, until it fades completely. This process, called gravitational redshift, means that from far away you see them slow, freeze, and vanish in silence. In truth, they have already crossed. But to you, the universe conspires to make their fall appear endless. Falling into a black hole isn't just about physics. It's about surrender. In every other fall, there is hope of resistance, a parachute to open, a ledge to grab, a ground to strike. But here, there is no bottom, no escape, no bargaining with gravity. It is the purest expression of inevitability in the cosmos. Once begun, it cannot be undone. And perhaps that's why black holes haunt the human imagination. They represent the idea of being caught in something larger than ourselves, something absolute, a destiny that cannot be resisted. But here's the twist. Black holes are not only destroyers, they may also be creators. The matter that falls in doesn't simply vanish. Its energy and mass contribute to the black hole, changing its spin, its size, its presence in the universe. And around the event horizon, strange things happen. Jets of energy erupt. Accretion disks glow with the brilliance of 1 trillion suns. In consuming, black holes light up the cosmos. They are both death and spectacle, silence and fireworks. So what does it really mean to fall forever? From one perspective, it means your journey into the abyss never ends, frozen at the horizon for eternity. From another, it means your plunge is swift, absolute, and final. In truth, both are correct. To fall into a black hole is to enter a place where forever and instantly are no longer opposites, but different faces of the same reality. Black holes are more than cosmic oddities. They are the purest distillation of gravity's power. They show us what happens when the rules of the universe are pushed to their breaking point. They remind us that space and time are not fixed, but malleable. That falling isn't always about reaching the ground. Sometimes it's about surrendering to the infinite.
In 2019, humanity gazed into the abyss, and for the first time, the abyss gazed back. The world was shown a picture, a blurry orange ring, a circle of fire surrounding a dark center. It didn't look like much at first glance, a fuzzy donut, some called it. But in that circle was a triumph of human imagination and persistence. It was the shadow of a black hole. Not the black hole itself, for that, by definition, cannot be seen, but its silhouette, its dark imprint against a glowing storm of light. For the first time, we weren't just theorizing, calculating, or imagining. We were looking. And that simple, imperfect image revealed secrets far deeper than its smudged edges suggested. For centuries, black holes lived only in equations. When Einstein published his theory of general relativity in 1915, he gave us a new way of thinking about gravity. No longer a force pulling masses together, but a bending of space-time itself. His equations suggested the possibility of regions where space-time curved so completely that not even light could escape. At first, even Einstein himself doubted such things could exist in reality. They seemed too extreme, too bizarre. Mathematical curiosities, perhaps, but not actual places in the cosmos. And yet, as astronomy advanced, evidence began to mount. Stars moved in strange ways, pulled by invisible companions. Galaxies spun faster than they should, hinting at massive hidden anchors. And at the centers of galaxies, something enormous and invisible was stirring. But how could we ever see what cannot be seen? The key was not the black hole itself, but its effect on light around it. A black hole's gravity bends light, pulling photons into curved orbits. Some are captured forever, some barely escape, smeared into rings of glowing fire. Together, this creates a silhouette, a dark circle where light cannot emerge, surrounded by a halo of radiation. This silhouette is what scientists call the black hole shadow. If we could capture this shadow, it would be the ultimate proof, a direct image of Einstein's equations etched into reality. But there was a problem. The shadow of a black hole is tiny. To see it, we would need a telescope the size of Earth itself. So humanity built one. Not a single telescope, but a network, stretching across the globe from the peaks of Hawaii to the deserts of Chile, from Spain to the South Pole. Together, these observatories formed the Event Horizon Telescope, a virtual instrument as wide as our planet. For years, astronomers prepared. They synchronized atomic clocks, aligned massive dishes, and gathered mountains of data, petabytes of information, far too large to send over the internet. Hard drives had to be physically flown between observatories for analysis. And then, in April 2017, they aimed their Earth-size eye at a single target, the supermassive black hole at the center of a distant galaxy, M87. When the image was unveiled in 2019, the world held its breath. There it was, a glowing ring, brighter on one side, encircling a shadow of darkness. To the untrained eye, it may have seemed underwhelming, but to scientists it was breathtaking. The size of the ring matched predictions. The shape was a near-perfect circle, just as relativity demanded. The brightness revealed the spin, the motion of matter swirling at near light speed around the abyss. It was, in every way, the black hole Einstein's theory foretold. So why was this blurry image so profound? Because it turned speculation into sight. For decades, black holes had been inferred from X-rays, from stellar motions, from jets of energy blasting into space. But these were footprints, hints, indirect evidence. This was different. This was seeing the outline of the abyss itself. And seeing changes everything. Think of Galileo lifting a telescope in 1609 and glimpsing the moons of Jupiter. Think of the first photographs of Earth from space, the pale blue marble floating in darkness. Each image shifted not only science, but perspective. The shadow of a black hole did the same. The image was more than a confirmation. It whispered secrets about the black hole itself. The brighter side of the ring showed that the black hole was spinning, dragging space-time in its wake. This phenomenon, called frame dragging, means that near a rotating black hole, space itself is twisted, pulled along like a whirlpool dragging water. The size of the ring revealed the mass, about 6.5 billion times the mass of our Sun. A giant among giants. The shape confirmed that Einstein's equation still held true even at the most extreme edge of the universe. And yet there was also mystery. Subtle details hinting at turbulence, magnetic fields, and plasma flows more complex than expected. The shadow wasn't the end of the story. It was the beginning. Beyond the science, there was something profoundly human about that image. It was blurry, imperfect, rough around the edges. But so are all first glimpses. Think of the first photograph ever taken, a smudged rooftop view from a Paris window. Think of the Wright brothers' first flight, a fragile machine trembling into the air for only seconds. The first image of a black hole is the same, a fragile beginning, proof that the impossible can be made visible. And like those earlier firsts, it opens a door. The Event Horizon Telescope has not stopped. It has already turned its gaze to the black hole at the center of our own galaxy, Sagittarius A star. And in 2022, the image was revealed, another ring, this time surrounding the giant at the heart of the Milky Way. Future upgrades may sharpen the images, even reveal the dance of matter in real time. Imagine watching gas swirl and vanish across the event horizon, like a storm dissolving into darkness. In time, we may even map the entire movie of a black hole's life. So what was the shadow's secret? It was not just a confirmation of relativity, not just a measurement of mass or spin. It was something deeper. It was the revelation that humanity, a species bound to a small planet, could reach across 55 million light-years and see the unseeable. That we could take an object of myth and mathematics and turn it into an image. It told us that the boundaries of knowledge are not walls, but horizons, meant to be approached, studied, and when possible, crossed.
The shadow showed us not only what lies at the center of M87, but also what lies at the center of human curiosity. In that glowing ring, we saw the marriage of physics and imagination. We saw the power of collaboration, thousands of scientists, engineers, and dreamers working together across the globe. And we saw, perhaps most of all, a reminder of humility, that the universe holds secrets vast and strange, and that our greatest discoveries are often not answers, but glimpses. A blurry ring of light, and in its center, darkness. The shadow's secret is simple, yet profound. Sometimes, to truly see the universe, we must look not at the light, but at the darkness it surrounds.
Have you ever wondered what it would feel like to hear the universe breathe? Not with sound, but with ripples. Ripples in the very fabric of reality. To discover them, we must begin with the nature of the dance. Black holes rarely live alone. They are not only destroyers, they are partners, companions, dancers. Many are born in pairs, when two massive stars die side by side in fiery supernovae, leaving behind two collapsed cores of infinite density. Over millions, even billions of years, these pairs circle one another, slowly, patiently. At first, their orbits are wide and calm. Two invisible giants locked in a silent ballet. But black holes radiate something subtle, not light, not heat, but energy carried away in gravitational waves. And every ripple they release carries just a touch of their motion away. Their orbits tighten, the dance grows faster, the steps become frantic, until finally, in the last seconds, they whirl around each other dozens of times per heartbeat. Then, in a final cataclysmic embrace, they merge into one. The collision releases a storm of ripples that spread across the cosmos. The universe itself quivers, as though space and time were a drum struck by the hands of giants. And here the question rises: how could we, fragile creatures of Earth, ever detect such a thing? For the answer, we must return to the dream of one man, Albert Einstein. In 1916, Einstein sat at his desk working through the consequences of his boldest idea, general relativity. He realized that if space and time were not fixed, but flexible, then massive bodies in motion must create ripples in that cosmic fabric, gravitational waves, like stones dropped into an invisible pond. But Einstein doubted we would ever hear them. The stretching and squeezing of space would be so faint, far less than the width of a proton, even after traveling across billions of light years. For nearly a century, their waves were theory alone, a hidden music of the cosmos, written on paper, but silent to our ears. Until one September morning in 2015. Across two observatories in the United States, known together as LIGO, the Laser Interferometer Gravitational Wave Observatory, a delicate experiment was waiting. 2 enormous L-shaped detectors, each with arms 4 kilometers long, lined with mirrors and lasers of almost inconceivable precision. On September 14th, the silence broke. Not with sound, but with a signal. 2 black holes, each about 30 times the mass of our Sun, had collided 1.3 billion years ago. Their merger sent ripples racing outward at the speed of light. And on that morning, those ripples finally reached Earth. LIGO's detectors twitched. A tiny stretching, a tiny squeezing, space itself moving. In that instant, humanity had opened a new sense, a new way of perceiving the universe. We were no longer deaf to the cosmic symphony. Since that first detection, LIGO, joined by Virgo in Europe and Kagra in Japan, has heard dozens more. Each one unique, each one a story told in the language of gravity. Black holes colliding, neutron stars merging, even the faint whispers of cosmic events far beyond our imagination. The universe is an orchestra, and gravitational waves are its music. But unlike sound, they do not fade in space. They carry the raw imprint of the event itself, the mass, the spin of the collision. Listening to them is like holding the echo of creation in your hands. Why should this matter to us here on our small planet? Because gravitational waves give us a way to explore what was once unreachable. Black holes hidden behind their event horizons reveal themselves in their dances. We can weigh them, measure them, even glimpse how they were born. And beyond that, gravitational waves may one day show us the very earliest moments after the Big Bang, when the universe itself first began to ripple. Imagine hearing the echoes of creation itself. The philosophy of the dance. There is also something profoundly human in all this. For billions of years, these cosmic dances played out in silence, no one to witness them, no one to listen. And then a species on a pale blue dot builds instruments of impossible delicacy. And suddenly, the universe is no longer mute. We hear it. We understand it. We become, in some sense, participants in the dance. It is humbling, and yet it is also empowering. Because when 2 black holes merge, the energy released in that instant is greater than the light of all the stars in the visible universe combined. And yet, across the void of time and space, those ripples reached us, fragile beings with fragile tools, and whispered, "I was here." So the next time you stand beneath the stars, remember, the universe is not silent. It is singing, and we are finally learning to listen.
The cosmic mirage, light at the edge of darkness. Have you ever wondered what it would look like to stand at the edge of nothing? Not just darkness, but a place where even light itself bends, twists, and refuses to go where it wants. This is the world of black holes. And at their edges, light performs its most extraordinary trick. It creates a cosmic mirage. The edge of darkness. Black holes are defined by a boundary called the event horizon. Cross it and escape is impossible. Not because there is a wall or a surface, but because gravity is so extreme, even light, the fastest thing in the universe, cannot break free. Yet just outside this edge, light behaves in ways that challenge our perception. It curves, it twists, it orbits. It creates illusions, bending reality into shapes that seem impossible. Astronomers call this region the photon sphere, a narrow zone where gravity is strong enough that photons can circle the black hole multiple times before escaping, like a marble rolling along a warped, invisible track. And it is here that the cosmic mirage appears. Bending light, twisting time. Imagine a flashlight pointed straight at a black hole. Instead of disappearing into darkness, the beam curves. Part of it escapes, looping around the black hole before continuing outward. If you were watching from a safe distance, you might see the light come from places it could never have originated. This is gravitational lensing, the bending of light by massive objects. The black hole acts like a cosmic magnifying glass, warping the background stars into arcs and rings. Some photons orbit several times, creating Einstein rings, glowing loops around the black hole, images of stars you would think are far away, folded into a circle around the abyss. And because time itself is warped near the black hole, the paths of light are stretched. A single flash of light can appear to last longer. Moments become elongated. The mirage is both a visual illusion and a distortion of reality itself. The first glimpse. The first time humans saw a black hole's shadow in 2019 with the Event Horizon Telescope, we glimpsed this mirage for the first time. That blurry orange ring wasn't just a boundary. It was the glow of superheated gas spiraling around the event horizon, bending light, twisting it, dancing along the curves of space-time. It was a visual confirmation of Einstein's theory, and a poetic reminder even the fastest thing in the universe can be trapped by gravity. The mirage is a boundary between what we can see and what we can never know. Reflections in the abyss. There is a philosophical dimension to this cosmic trick. We think of light as the ultimate messenger, a way to see the world, to know what is happening. Yet here, at the edge of a black hole, light lies. It deceives. It shows us what isn't there, bends reality into illusions, forces us to question what we know. In a sense, the cosmic mirage mirrors human perception itself. What we see is not always what is true. Shadows, curves, and reflections can trick our eyes, just as gravity can trick the path of light. The dance of matter and light. The mirage is not only created by light, it is shaped by matter too. Matter falling into a black hole forms a swirling accretion disk, gas and dust heated to millions of degrees centigrade. It glows intensely in X-rays, visible light, and radio waves. As the disk spirals inward, its light is bent, smeared, and twisted by the immense gravity. The result is a kaleidoscope of color and motion. Light from the back of the disk wraps around the black hole to the front. The side moving towards us appears brighter, moving away appears dimmer. A single point of matter can appear multiple times, stretched into arcs, loops, and rings. It is a cosmic mirage, a hallucination of physics, a visual symphony written in light and gravity. why we study it. These illusions are not mere curiosities, they are windows into the most extreme environments in the universe. By studying the distortions of light near black holes, astronomers can measure the black hole's spin, its mass, and even the behavior of matter in conditions we cannot replicate on Earth. The cosmic mirage is a tool, a way to see the invisible. It allows us to test our theories, to push the boundaries of knowledge, and to glimpse the universe as it truly is. Strange, beautiful, and beyond comprehension. A lesson for humanity. There is also a humbling lesson in these mirages. We are creatures of light. We see, we perceive, we rely on photons to tell us the story of reality. Yet the universe reminds us that what we see is only a fragment of the truth. At the edge of darkness, reality itself becomes flexible. What we see depends on perspective, on path, on motion. What we trust, light can deceive. Perhaps there's a metaphor here for our lives, for knowledge, for curiosity. To approach the unknown is to confront uncertainty. To peer into the abyss is to learn how fragile and precious our perception truly is. The cosmic mirage is a vision at the boundary of understanding. It is light twisted, curved, and delayed, creating illusions that teach us both science and humility. When you look at the night sky, remember that light is not always what it seems, that the universe can bend reality, stretch time, and create images that defy intuition. The edge of a black hole is not just darkness, it is a mirror, a teacher, a cosmic storyteller, whispering that reality is stranger than we imagine, and that even at the edge of darkness, there is beauty, there is motion, and there is light, bent, twisted, and eternal.
Please consider liking this video, sharing it with others, and subscribing to our channel for more awe-inspiring explorations. We'd also love to hear from you in the comments below. Where in the world are you watching from, and what time is it for you right now? The hunt for primordial black holes. Imagine the universe as it was, just moments after the Big Bang. A hot, dense sea of particles, light, and energy. Chaos and creation intertwined. In that primeval firestorm, there may have formed something extraordinary. Black holes unlike any we see today. Tiny, ancient, and elusive. These are primordial black holes, phantoms of the early cosmos, hiding at the edges of observation, whispering secrets from the dawn of time. The birth of the first shadows. Primordial black holes are not born from dying stars. They are older than stars, older than galaxies, older than the familiar cosmic structures we know. In the first fractions of a second, the universe was dense enough that small regions could collapse under their own gravity, forming black holes with masses ranging from less than a gram to thousands of solar masses. Imagine it, a universe still young, light barely streaming, matter barely forming. Yet pockets of extreme density collapse, creating objects so compact that nothing can escape. Black holes that have existed longer than anything else. Some theorists suggest that these primordial black holes might be a component of the universe's mysterious dark matter. Silent, invisible, and almost impossible to detect. They could be scattered throughout galaxies, influencing motion without revealing themselves.
The hunt begins. How do you search for something that is essentially invisible? Astronomers employ ingenious methods. They look for the effects on nearby stars or gas clouds. They search for microlensing events, moments when a hidden black hole passes in front of a distant star, bending its light and revealing its presence briefly. Sometimes the clues are subtle. A flicker here, a shift there, a whisper in the cosmic microwave background. Every anomaly is a potential hint, every shadow a phantom waiting to be identified. The hunt is patient, slow, frustrating, yet profoundly human. For centuries, we have looked at the night sky and wondered, what is unseen and why? The significance of primordial black holes. Why does it matter if these ancient black holes exist? Because they could answer questions we have struggled with for decades. They might explain dark matter, the invisible substance that binds galaxies yet refuses to shine. They might give us clues about the conditions of the early universe, the fluctuations in density, the physics at energies far beyond what our particle accelerators can replicate. Every detection, even indirect, would be a time machine, a window to a universe that existed billions of years before our sun, before Earth, before life. Listening for the phantoms. Some of the most promising signals come from gravitational waves. When black holes merge, even primordial ones, they send ripples across space-time. LIGO and Virgo, instruments designed to detect mergers of stellar black holes, may one day detect these faint whispers from the distant past. The signal would be subtle, rare and fleeting, but it would carry a story older than any star, a story of creation, of collapse, of a universe still finding its shape. Each wave would be a footprint of a black hole that has existed for nearly the entire history of everything. The philosophy of phantom horizons. There is a poetic side to this hunt. Primordial black holes are ghosts of the cosmos, reminders that the universe has been mysterious since its first moments. We search for them not just for knowledge, but for connection, to witness something that has existed longer than any living thing, longer than any light we can see. They are mirrors of our curiosity, our relentless desire to uncover the hidden, to map the unseen, to understand what lies beyond immediate perception. The universe is full of horizons, edges where understanding fades. And these primordial black holes are phantom horizons, challenging us to stretch our imaginations, our instruments, and our courage. Reflections on the hunt. Even if we never detect a primordial black hole directly, the hunt itself teaches us something profound. It reminds us that the universe is older, stranger, and more intricate than we often imagine. That what we see, galaxies, stars, light, is only part of the story. That darkness, silence, and invisibility are just as real as illumination. And it reminds us, most importantly, that human curiosity has no bounds, that across centuries we continue to look, to imagine, to seek answers in the void. So, when you look up at the night sky, consider the phantoms that may be hidden there. black holes formed before the first stars, shadows older than galaxies, ghosts of the cosmos quietly shaping the universe from behind a veil of invisibility. The hunt for primordial black holes is more than science. It is a meditation on time, on existence, and on the limits of perception. It is the story of a universe that is far older and more mysterious than we can fully grasp, and of a species that dares to understand it. And perhaps in the whispers of these ancient horizons, we can hear a message. The universe is eternal. The mysteries are infinite, and the search itself is a kind of discovery.